One of the most common question, complaint, whinging I get on the channel is about the VRAM of the GPU cards. We all know that we don't have huge GPU cards with VRAM or virtual memory to run all of these huge large language models. That is why people invented quantization. What quantization does is it reduces the size of the model from full precision, which is floating point 32, to int 8, int 4, and even lesser than that, so that the model would be able to fit on the limited amount of VRAM. So if you don't have huge or biggest or expensive GPU card, you can always use a quantized version of the model. And there are various tools like Olama, you can use LM Studio, and there are various formats of this quantized versions of the models. In this video, we are going to discuss this GPTQ model tool, which is a toolkit to allow you to convert a full model into a quantized model with GPTQ format. Now, quantization reduces the precision of model weights and activations from float 32 to lower bit representation, as I mentioned. It decreases the model size and memory usage, but there is a slight hit on the accuracy of the model. But I think if you are using a good quantization level, you should be able to get a fair good idea of the model. And I have seen people even using a quantization level of Q8 and something like that on in the production environments. This tool, GPTQ model, is a fork of AutoGPTQ library, which implements the GPTQ algorithm. GPTQ algorithm is a post-training quantization technique where each row of the weight matrix is quantized independently to find a version of the weights that minimizes the error. These weights are quantized to int 4, but they are restored to floating point 16 on the fly during inference. This can save your memory usage by 4 times because the int 4 weights are dequantized in a fused kernel rather than a GPU's global memory. And you can also expect a speed up in inference because using a lower bit width takes less time to communicate. And that is this GPTQ model has taken it to another level where it has made a lot of improvements. This GPTQ model is different from GPTQ in a sense that it is an opinionated fork refactor of AutoGPTQ with latest bug fixes, more model support, faster quant inference, faster quantization, better quants, and a pledge from the Model Cloud team which has created it that they are going to keep this library up to date with the latest advancement, model support, and bug fixes. So that is quite interesting. By the way, GPTQ is not the only format for quantization, it is slightly even old too. There are a lot of other formats like AWQ, GGUF, AQLM, Quanto, WTQ, HQQ, Optimum, Torch AO, and I have covered all of them separately on the channel in the past. So please, if you're interested, just search the channel and you should be able to find other quantization formats. But we are focusing on this GPTQ in this video. We are also going to install it locally, and then I will also do a quantization of a model to show you how you can quantize any model out there to be run on a limited amount of VRAM. Before I do that, let me give a huge thanks to Massed Compute who are sponsoring the VM and GPU for this video. If you are looking to rent a GPU on affordable prices, I will drop the link to their website in video's description, where you will also find a coupon code of 50% discount on a range of GPUs. So do check them out. I am sure you will like them. Okay, so this is my Ubuntu 22.04 and this is my GPU card NVIDIA RTX A6000 with 48 GB of VRAM, courtesy Massed Compute. Let me clear the screen. Let me create a virtual environment Conda. I'm just calling it GP. Let's wait for it to get installed. It is going to take a minute or so. The virtual environment is created. Let's install some of the prerequisites like torch and transformers and accelerate. All the prerequisites are done. Let me clear the screen. And now let's git clone the repo of this tool, which is GPTQ model. and we have seeded into it. And I'm just installing it from the source to make sure that we have the latest version. So this is going to take a bit of a time, so let's wait for it to finish. Eventually, the GPTQ model is installed, and you won't believe it took around 50 minutes to run this installation. I mean, I just ran that command, it went on for 50 minutes. I think this is one area they badly need to improve, because no one is that keen to install a tool which takes 50 minutes anyway. So let's see, let me launch my Jupyter notebook and then we will see how it works. This is going to install the Jupyter notebook and launch it in the browser. It seems my Jupyter notebook is having issues with this CUDA version. So instead of spending time to fix the Jupyter widget, what I'm going to do, I'm just going to launch my Python interpreter. To keep things simple, I'm just going to install it here or use it here. So first up, I'm importing the auto tokenizer, and then I'm just importing this quantize config. You can ignore these warnings. And then as a sample, I'm just picking up this Facebook's very small OPT 125 million parameter model. And then this is where we want to put our new quantized version of the model. Next up, let me grab the tokenizer of the model, and that is also done. Let me clear the screen just so that it would be easier to read it. Next up, let's define a calibration data set which we will be using. You can of course put anything there. I'm just, for the purpose of completion, I have just put in one line. It could be the whole full data set if you like. Okay, so let me run it. And that is done. Next up, let's define the quantization config. Sorry, not this one. Let me remove this. So this is a quantization configuration which I was referring to. So bits is 4 means that this is a bit width for quantization. In this case, 4-bit integer representation is used instead of the default 32-bit full representation. This reduces model size and computational requirements. And the group size is 128. That defines the group size for weight quantization. This means that groups of 128 weights will be quantized together, sharing the same scaling factor. This helps maintain accuracy. So let me define it. That is done. Next up, let's define the model, and we are grabbing that model which we specified above, and we are loading into our GPU. If you don't have GPU, it is going to load into your CPU. So this is a PyTorch model. That's done. It's a very small model. And now in order to quantize it, all you need to do is to run this command model.quantize on that calibration data set. And you can see that it is now going layer by layer, and then it has started the quantization. Shouldn't take too long because it's a very small model, very small calibration data set. So let's wait for it. It is still progressing through the layers. And there you go, all done. And it has also put in some of the statistics, lot of mumbo jumbo around numbers, but you see how quick that was to quantize this huge model. Now you can save that model locally. Let me clear the screen quickly. And then you can simply save it by giving that output directory. And after save is finished, you will see that in this directory, in your OPT125 mil 4-bit, in your root of this GPTQ model, this is the new model which is just half of the size, around even less than half, 125 meg. So this is how you can use this to quantize any model into GPTQ format. So play around with it. Let me know what do you think. If you like the content, please consider subscribing to the channel. If you're already subscribed, please share it among your network as it helps a lot. Thanks for watching.